Hello all. So in this lecture we will continue our analysis of the common indoor air pollutants. We will look at some of the pollutant specific methods and some detection methods or detection instruments. First we will go to the organic pollutants. These pollutants, these organic compounds could be sort of very volatile or the normally volatile or the semi-volatile organic compounds and the compounds that are sort of associated with the particulate matter, particulate organic matter, let us say. VOCs can be commonly collected on the solid sorbents, and this can be followed by thermal desorption or solvent extraction. Thermal desorption would mean the VOCs are adsorbed. So the sample passes through the sorbent, the VOCs become adsorbed, and then the sample flow is stopped. Then a reverse airflow is made from a clean air, and the tube, the sorbent, which is now containing the VOC, is heated, and in that heat the VOCs are now emitted, and then they are measured through any of the analysis methods. So the sorbents that are used with thermal desorption include 10xTA, chromosorb, graphitized carbons, carbon molecular sieves, and multibed combinations. In solvent extraction, we will have the sorbent which has collected the VOC, which has adsorbed the VOC, and then we pass solvent through that sorbent, and the VOC will get extracted, and then this extract can be analyzed with another method. So the sorbents that are used with solvent extraction method include the silica gel, activated charcoal, Anasorb 747, carboxyls, which are basically synthetic carbon, porous polymers, and some carbon molecular sieves. This is how a sorbent tube will look like. So first, when the tube is not in use, we will have these sealed caps at the two ends, which will prevent the contamination of whatever is inside. Now this is the flow through from this top to bottom. So first we have a high purity glass wool which may give a uniform pressure drop and may also trap any sort of particulate matter, because we want to analyze, let us say, VOC, volatile compound, gaseous compound. So we want to also protect our sorbent. So PM is going to be trapped here, let us say. Then we have the sorbent layer, which is precise, which has a very known, or let's say precise surface area, pore size, adsorptive characteristics, because we want to adsorb certain compound, so we need some certain adsorptive characteristics, and the mesh size. So the air comes and let us say the VOC is supposed to be trapped here. Then we will have a foam separator and some backup sorbent layer. Now if our sorbent is perfectly aligned, or our sorbent is perfect and has not saturated and the flow is not too high, all the VOCs are going to be trapped in this layer. So ideally, as the air passes through this layer, it should be free of any VOC. So we have this backup sorbent layer which can detect any breakthrough, meaning if some VOC was not trapped and reaches here, that means our collection efficiency in the main sorbent layer is not 100%. If some has reached here, who knows, some will reach outside, and then basically we are not detecting the correct amount. So ideally there should be no VOC in this sorbent layer, or no organic compound. If not VOC, whatever we are analyzing, the gaseous compound, it should be adsorbed in this layer and nothing should arrive at this layer. And this is how this may look in the in the real tube: glass wool, sorbent layer, and then another separation, and then another smaller sorbent layer, which is just used as a check that our main sorbent layer is working properly. Once collected, analysis may be carried out by gas chromatography, which is coupled to different detectors, which could be mass spectrometer, or diode arrays, flame ionization detectors, electron capture detector, maybe spectrometer, photoionization detector, photoacoustic spectroscopy. FID is already done, PID also done, photoionization detector. Sometimes they may be analyzed during LC or HPLC, MS, or non-dispersive infrared and Fourier transform infrared spectroscopy methods. Pesticides. Pesticides can be extracted from, let us say, the sorbent cartridge or any other collection mechanism and determined by GC, gas chromatograph, equipped with an electron capture detector, or maybe nitrogen phosphorus detector, flame photometric detectors, or mass spectrometer. For some pesticides, HPLC coupled with UV detection can also be used. It is known that PCBs can interfere with some of the pesticides, but column chromatography can be used to separate PCBs from such pesticides. Polycyclic aromatic compounds, PAHs, phthalates and phenols. Sometimes sampling of PAHs typically may require use of quartz fiber filters and sorbents, and these PAHs can be suitably analyzed by GCMS, HPLC or UV based fluorescence detections. GCMS schematics is something like this. We have the auto sampler here, which injects the sample. We have an inert carrier gas, which is the mobile phase. It goes through certain traps, and it is required that they may be clean of at least the analyte, and generally high purity gases are used. Then it arrives at injection area. An auto sampler, and also it could be a manual sampler. This is where the sample is injected to the inlet, and then the carrier gas takes it to the column. The gas chromatography, and this is a so when the carrier gas containing the alanite goes towards this column, the compounds are separated. Then they are transferred to the, in case of MS, to the mass spectrometer, or in case of any other detector, to the other detector. So we have an ion source here, and after that the compound is fragmented and goes through the mass analyzer and ion detector, and this information is taken to the computer to give us a chromatogram, so that we know which compound has been eluted. And so each compound has a different retention time in the column. So depending on the retention time, we can check how much compound has come out, and we can, using calibration curves, calculate the concentration of the compound. So mass spectrometry, in mass spectrometry, the sample is converted to sort of rapidly moving positive ions. So let us say this is our gas sample injection port, and here we have the electron beam and the sample vaporizer. So when through this ion bombardment, we have the positively charged fragments of the analyte in question. This is accelerated, and in the presence of a magnetic field, they are separated according to their mass to charge ratios. So given a same charge, the heavier atom will be deflected less compared to the less heavier atom, which will be deflected more if all of them are at the same charge. So the separation is basically dependent on the mass to charge. Then we have the analytical liquid chromatography, which is used to separate components in basically a liquid based system. HPLC is sort of, and then the principle is the same as chromatography, and the separated analytes can be again measured in a mass spectrometer. So HPLC is just an improved form of traditional liquid chromatography, in that the solvent is forced under high pressures compared to the traditional liquid chromatography. If done with the UV detector, we will measure the absorbance of monochromatic light of fixed wavelength in the UV, or sometimes UV vis detector, then visible wavelength range, against a reference beam. And then we can compare the absorbance in the UV or visible range and the reference beam, and calculate how much absorbance has happened, and then relate it to the concentration of the analyte. So if we have more analyte, we should have more absorbance in the said wavelength range. So we should know, of course, the wavelength range at which the analyte will absorb radiation. UV detection can be used for analyzing unsaturated bonds, aromatic groups, also functional groups containing heteroatoms. Then we have the diode array detectors, which are optimized for rapid simultaneous acquisition of a full spectrum, UV visible light spectrum, with a spectrophotometer. It is same like a single dispersive instrument, but the grating is after sample to directly disperse the transmitted light. We will cover this in the next slides more, like in a figure framework. The transmitted light of the sample illuminates the array detectors simultaneously, and they will allow a fast data collection. So the source will basically illuminate the sample in pretty much all the light wavelengths, because we will use a combination of lamps. The detector will utilize generally two light sources emitting a broad spectrum directed through the sample. Under high pressure, the sample will move through a flow cell in the detector's optical path. This will facilitate the interaction of the sample with the light that is being incident on the sample. Then we have an array of diodes which will be sensitive to the specific wavelengths of light, and together this array of diodes will cover a broad range of wavelengths. So we can analyze a lot of wavelengths. So as light penetrates the sample, the various analytes will absorb light at their respective wavelengths. So basically we will pass all the light wavelengths, and different analytes will absorb different wavelengths. For each target compound in the sample, our diode array detector could measure light intensity at their particular wavelength, for the wavelength which is specific for the target compound. So in one go, we may be able to identify and also quantify to some extent a lot of components in the sample. So this method will give us a very detailed information about the sample composition itself, because we have basically analyzed the whole wavelength spectrum. This is how it may look like conceptually. So we have basically two lamps, deuterium lamps and tungsten lamps, and then we have a grating which goes to the diode array. So here is our source, this is the entrance slit, and this is the dispersive device, and this is a monochromator, and the sample. Now for each of the wavelength we can pass, the light passes, and for each of those wavelengths the detector will check what is the absorbance. So we are able to, various analytes will absorb light at distinct wavelengths. So for every wavelength, if the analyte is present, there may be some absorbance, and according to looking at the absorbance, we can go back and see what kind of, go back to the literature and see, or previous data and see that which analyte might be present. And these days we will have libraries that so and so analyte at so and so wavelength, and the libraries may come itself with the instrument. The other detectors, one of them is flame ionization detector. In this detector, a hydrogen flame is created by burning hydrogen and air. A sample which usually will be containing carbon will be oxidized by the flame. Basically, it works on the principle that the ions are liberated. So in this flame, the ionization of samples occurs, and then the liberated ions are collected on the collector electrode. And when these ions are collected on this electrode, we will have an electric signal which we can relate to the concentration of the analyte in the sample. So this is how it may look like. So this is a flame ionization detector. So this is our column and the sample has arrived. Then we have H2 and makeup gas and then air here. And we there is a nozzle that will sort of force and aerosolize, and we have the hydrogen flame. This flame, once the sample goes in this flame, it's going to be oxidized and ionized. Then these ions will be collected on these collector plates, and which will be collected to an electric signal and then goes to data processing. For example, here we see organic matter is burned in the hydrogen flame, and then several ppm of organic matter will turn into the ions. So for example, here CH being oxidized or CN being oxidized, and when these electrons will be going, these ions will be going to the detector. When these ions gather in the detector, a current will flow, and we can relate this current to the concentration. This is another sort of schematics. So air is going, gas sample is going, and hydrogen is going, and we create a flame, and then the ionized sample goes to the collector, where we will have this voltage, and we can check how much is the current flowing when the ions are going to the detector, and then we have the sample exhaust. The next is the photoionization detector. This basically applies ultraviolet light to the detectable gas for ionizing the gas and causing an ion current to be generated, and then a sensor measures this current for determining gas concentration. So here we have the detectable gas, which is the gas to be measured coming in the ionization chamber. Here we have the UV light source. So the gas gets, the analyte basically gets ionized. So we have M plus going here, E minus going here, and the current will be generated, which will be proportional to the amount of analyte that was ionized. So we can relate this current to the concentration of analyte that is in the sample, and then the gas of course is released to the other exit. We have another method called photoacoustic spectroscopy. The principle is this, that when a modulated infrared light beam is absorbed by the sample, heat is generated due to the incident light. So we have this sample here in a sealed chamber, and we have the infrared light coming in, and we could have some inert helium gas, for example. Now heat causes pressure changes in the surrounding gaseous layer, which is then detected by the highly sensitive microphone. So this is our microphone. The signals from the microphone are basically the acoustic interference waves, and the acoustic waves produced will be a measure of the concentration of the analyte. Then we have another detector called electron capture detector, and this is quite specific to organochlorines in general. The principle is that the ions are detected when reading the changes in voltage value that will maintain a constant ion current, ion gathered at the collector. So here nitrogen is used as a carrier gas, and this is ionized by beta waves emitted from a nickel radiation source. So there will be a radiation source in this electron capture detector. This is the gas coming from the column, and nitrogen is our carrier gas. It goes in this area. So nitrogen gets converted to N2 plus and E minus. So a current will flow when the ions will come to this collector. When we have an electrophilic compound such as chlorine, so that's why it is specialized for organochlorines. So we have a polychlorinated biphenyl compound here. So PCB will take up this electron and become PCB minus. So PCB minus will take more time to reach this collector, and then a higher voltage will be needed to maintain the same constant ion current to flow. So this higher voltage, so the more the PCB, the more voltage may be required, and in that sense we would be able to gauge the concentration of PCB or the concentration of organochlorine in the sample. We have other methods as well. These may include methods such as proton transfer reaction mass spectrometry, in which the first stage includes ionization of the gas phase VOC molecules by the transfer of a proton from H3O plus to the VOC molecule. So VOC plus H3O plus gives VOCH plus H2O. This VOC ion, VOCH plus produced in this reaction are subsequently detected by a mass analyzer. So we have this mass spectrometer here. Generally, not all the compounds can be detected. That basically depend on the proton affinity. The proton having higher proton affinity than water will undergo proton transfer reaction with H3O plus and are detectable in this real time. So if we have these different compounds, alkenes, aromatics, alcohols, aldehydes, ketones, acids, nitriles, amines and sulfides, there are some compounds which will show no, and this is our proton affinity, and this is the proton affinity for water. So these compounds don't show any reaction: butane, ethene, propane, ethane, methane. This is the proton affinity for H2O2, and there will be proton transfer if we go from this to up, and we will have propane, benzene, formaldehyde, formic acid, acetic acid, toluene, xylene, and beyond H2O2 we have DMS, methylamine, dimethylamine, trimethylamine, and these can be detected well. Then in real time we also have chemical ionization mass spectrometer, which is a advanced mass spectrometry technique. It basically involves instantaneous adopting instant ion molecule reactions and simultaneous detection of multiple substances through the switching of reaction ions. The instrument is a system of different pump stages where the ambient air is introduced by a critical orifice into the ion molecule reaction chamber. Different reagent ions can be introduced in this method in orthogonal direction from orifice depending on the target analyte of interest. We also have trace organic gas analyzers, which are sort of fast online GCMS systems. They have a cryogenic pre-concentrator, a gas chromatograph, a mass spectrometer and a zero air calibration system. and the nature of columns may vary depending on the VOC of interest. After this, we have sort of a class we would say odor monitoring. Here, this is to detect odors caused by different VOC mixtures or inorganic odorants like hydrogen sulfide, H2S, and ammonia. Then we will go into particulate matter, and we have many techniques for measuring particulate matter. They can be characterized generally as filters based gravimetric samplers that will collect PM into a filter, and the filter needs to be weighed before the start of sampling and then at any period of time when we need to make a measurement. We also have direct reading instruments that will provide continuous measurements for PM concentration in ambient air, and sampling interval of these instruments can be in seconds and even can be in minutes, but very fine to quite fine resolution compared to the filter based samplers where we may have to put the sampler in the field for quite some time. Example here is high volume samplers. So basically in this is how a sampler may look from the front, and this is a box which will close. The principle is that the air is passed through specially designed inlets that will only allow particles of certain size bins. For example, a PM10 sampler will have a cutoff PM10 diameter of 10 micrometer, and we have learned about this cutoff diameters PM10, PM2.5 definitions in the week on aerosols. So these samples may allow only PM10 to pass through, and then they will pass through the filter, and the filter size can be as per the procedure for the standard test we want to do, or if we want to do research, we can use another filter pore size. We can use 2 microns, we can use 0.5 microns or any microns, but we should be aware of what the purpose of the experiment is. So a PM10 sampler will sample PM sort of less than 10 micrometer up to the size of the filter pore. The PM2.5 will allow passing of fractions 2.5 or lower, of 50% of 2.5 and all the lower, and up to the size that is of the filter. So it could be 2.5 to 0.45 or 2.5 to 0.22 microns, depends on the filter pore size we are using here. High volume, because these samplers will suck a lot of volume, because the concentration of PM in air may not be very large or very huge in many parts. If the air is pretty clean, then we need to pump a huge amount of air volume to get measurable particulate matter. So we need a high volume of air sampled in a shorter time, and hence the term high volume sampler. So the process would be that we would sort of pre-weigh the filter, or we will dry the filter and pre-weigh them and then install them and then run the sampler and then again dry the filter and check the change in mass, so we know how much dry particulate matter has been absorbed. Or we could try another methods, only we need to have an initial and final condition, and we should know precisely what we are measuring. The items below are basically flow sensors to maintain the volumetric flow, and then the air outlet. The filters can be anything, they can not must be. The filter may be glass fiber filters, quartz fiber filters, polytetrafluoroethylene or PTFE filters or PTFE coated glass fibers. But filters must be carefully conditioned before collection and after collection, so that we have standard conditions of comparing the before and after value. And by this we can basically say how much particulate matter in whatever size range we are looking at is present in the air which we sampled. Then the average concentration, so average meaning the average over the collected period of time. if we ran the sampler for 1 day, then what we will report is a 1 day average, because all the sample in that 1 day has come into the single filter. So the average concentration will be estimated by dividing the weight gain of the filter by the total volume sampled. So we will have mass per meter cube, let us say. In cases where we also want to do chemical analysis in addition to the mass gravimetric analysis, we need to use special filter materials that do not interfere with the sampled gases, and the analytical procedure should be adopted suitably. Then we have this tapered element oscillating microbalance analyzer. The principle is that the oscillation frequency of the tapered glass tube is proportional to the mass of the tube. So here we have this mass transducer tapered element. So PM when deposits, so this is our tapered element oscillating microbalance. PM is coming in. Here we have, let us say, PM10, but it could as well be PM2.5. There is some flow splitter, and then we have this mass transducer. The PM deposited on the tube will change the mass of the tube and the oscillation frequency of the tube. So then we have some frequency. So here we will have amplifier to amplify the frequency so that it may be counted. So we will have amplifier and frequency counter. The measurement of the oscillation frequency change of the tube and the volume of the air sampled will enable us to assess the mass concentration of PM in the air that is being sampled, and this mass concentration could be micrograms per meter cube units. Denuders for particulate matter may allow for separation of gases from particulates and minimize the interferences. And we can have sodium carbonate, sodium hydroxide and potassium hydroxide that can be coated on the surface of a denuder. So they can remove basically the acidic gases. Then we have several methods for analysis of collected particulates, such as X-ray fluorescence, proton-induced X-ray emission, neutron activation analysis, absorption and ion chromatography for chemicals, or for analysis of chemicals in the particulate matter itself. So we have to be careful to judge which method we are going to use for which purpose. If we just want to use or calculate particulate matter, we can as well use a high volume sampler or one of the other methods which can just give us the an answer, rather than using denuders or any other kind of things. But if you want to do the chemical analysis of the particulate matter, then we may have to go to particulate matter collection, analysis, and then further analysis. We have beta attenuation analyzers that deduce particulate matter on filter by measuring radiation intensity of filter with collected PM. So air is first sampled through a size selective inlet, PM10 or PM2.5, with or without heater or dryer. So that depends on what we are analyzing. Then air is passed through a paper filter which collects the PM. The paper filter, basically this one, is exposed to a beta attenuation source, and then we can gauge how much is the PM concentration in the filter or PM mass, and then we know how much was sampled and we can derive the PM concentration. The black smoke technique may measure PM based on darkness of filter paper measured by a reflectometer, and then it is converted to a concentration of PM. Then we may have optical analyzers that may utilize the reaction between ambient PM and imaging, laser or infrared light. They can be classified as direct imaging, light scattering and light obscuration, nephelometer type analyzers. In a direct imaging particle analyzer, a beam of halogen light illuminates the particles and the shadow of each particle is projected to a high definition, high magnification, high resolution camera. The camera will record and the video is analyzed by software to measure the PM's attribute, which could be size or shape or color or concentration. Then we have the light scattering analyzers, which will use high energy lasers as the light source. So when a particle passes through the detection chamber, laser light is scattered by the particle, and then the photodetector will detect the scattered light, and the intensity of the scattered light will enable the understanding of particle size and particle count, and this will provide us with the information on the PM concentration. The next is a nephelometer, and we would have used this in the lab also. In this, a near infrared LED is used as the light source, and a silicon detector is used to measure the total light scattered by the PM. Then analyzing the intensities of the scattered light and the shape of the scattering pattern will enable us understanding the size distribution and the mass concentration in the analyzed sample. So in summary, we have covered several sampling strategies, sampling and extraction methods, and instrumentation and analysis methods. Of course, there will be many more methods that are possible, and with this the aim is to give the viewer an overview of what methods can be possible, and then the viewer may go on further and learn more and more methods and use them for the specialized application they are looking for.